Our heart is an exciting organ. In this animation, we show the picturesque complexity and mechanical simplicity of the human heart. The human heart lies well protected in the chest behind the ribs and sternum. To the left and right are the lungs, which absorb oxygen from the air we breathe. The heart's task is to pump oxygen-poor blood through the lungs and then transport the oxygen-rich blood coming from the lungs into the rest of the body. Let's take a look at the basic anatomy of our heart. Blood enters and exits the heart through several large blood vessels. The aorta has been considered an independent organ since February 2024. The heart receives deoxygenated blood from the body through the inferior and superior vena cava. It pumps this blood to the lungs with the help of the pulmonary artery. The oxygenated blood from the lungs returns to the heart through the 4 pulmonary veins. The heart then pumps this blood into the body by the aorta. However, the heart itself is not supplied with blood with the help of the aorta. The coronary arteries are embedded in the epicardial adipose tissue. The heart supplies itself with oxygen and nutrients through these blood vessels. There are 2 coronary arteries, which supply the heart with oxygenated blood, and the coronary sinus, through which the deoxygenated blood flows back into the heart. A heart attack can occur when the coronary arteries become blocked, narrowed, or completely obstructed. Blood can then no longer flow freely, and oxygen and other nutrients cannot reach the heart muscles. Let's first take a look at the internal structure of the human heart. The coronary arteries just shown originate from the main artery, also known as the aorta. The openings of the arteries are located above or at the aortic valve, which consists of 3 semilunar cusps. The aortic valve is located at the end of the aorta. The pulmonary valve is located at the end of the pulmonary artery. Rarely, the valves have 2 or 4 cusps. The heart has 2 other valves that consist of leaflets, or cusps too. The mitral valve consists of 2 leaflets, and the tricuspid valve has 3 of these leaflets. When the tricuspid valve opens, deoxygenated blood flows from the right atrium into the right ventricle. The deoxygenated blood then flows through the opened pulmonary valve and then enters the lungs via the pulmonary artery. The oxygenated blood from the lungs passes from the left atrium into the left ventricle through the mitral valve. When the aortic valve opens, the blood enters the body via the aorta. The blood flow is controlled by the muscles of the heart. The muscles contract and then relax again. At that point, we show a simplified version of the pumping process. Later, we will describe the process in more detail. When the atria of the heart contract, the atria's space becomes smaller. The resulting pressure causes the blood to push the leaflets towards the ventricles. This allows the blood to be pumped from the atria into the ventricles. When the muscles of the atria contract, the muscles of the ventricles relax. And when the muscles of the ventricles contract, the muscles of the atria relax. The contraction of the ventricular muscles creates high blood pressure, which pushes the leaflets towards the atrium. However, the leaflets have thin fibrous cords that prevent the leaflets from being pushed into the atrium. These chordae tendineae are attached to papillary muscles that contract at the right moment. The contraction of the right ventricular muscles causes the pulmonary valve to open. This ultimately transports the blood to the lungs via the pulmonary artery. Now let's take a look at the left atrium and the left ventricle. The left ventricle's task is to pump oxygen-rich blood into the entire body. To achieve this, the left atrium first pumps the blood coming from the lungs into the left ventricle. The muscles of the left ventricle then contract. As in the right ventricle, fibrous cords and muscles prevent the leaflets of the valve from being pushed into the atrium. In the left ventricle, the muscle columns known as trabecular carneae are particularly well developed. The resulting pressure opens the aortic valve and the blood is pumped through the entire body with the help of the aorta. In this simplified illustration, we can clearly see how the blood is pumped through the body's blood vessels. The left ventricle, just shown, supplies the entire body with oxygen-rich blood via the aorta. Head, abdomen, arms, and legs. That way, nutrients, oxygen, immune cells, waste products, and much more are transported from one place to another. The arteries transport the blood away from the heart, and the veins transport the blood towards the heart. The returning blood then reaches the right atrium of the heart via the inferior and superior vena cava, and from there into the right ventricle. The right ventricle then pumps the deoxygenated blood into the lungs with the help of the pulmonary artery. Here, the blood absorbs oxygen, enters the left atrium, and finally returns to the left ventricle and the aorta. The anatomy and function of the lungs can be seen in the colorful animation on this channel. As the pulmonary circulation is short, but the systemic circulation is long, the heart chambers require muscles of different strengths. For this reason, the right ventricle has a much thinner muscle layer than the left ventricle. The interventricular septum of the heart, which separates the left and right ventricles, also consists of strong muscles. The atria have muscles too. The fine parallel muscular ridges, which scientists refer to as pectinate muscles, can be found particularly in the right atrium. In contrast, the left atrium with its atrial appendage has more of a smooth structure. As we have previously only shown a simplified cardiac cycle, we will now take a look at the actual process showing the right side of the heart. The muscles of the atrium and ventricle are relaxed. The tricuspid valve is open. The pulmonary artery is closed through the pulmonary valve. Contracting the atrial muscles initiates atrial systole, which pushes blood from the atrium into the ventricle. The atrial muscles then relax and the ventricular muscles contract. The resulting pressure closes the tricuspid valve. The ventricular muscles contract further and increase the pressure, opening the pulmonary valve and forcing the blood into the pulmonary artery. When the ventricular muscles relax again, the pressure inside the ventricle drops. This causes the pulmonary valve to close, as the pressure in the pulmonary artery is higher than the pressure inside the ventricle. The tricuspid valve opens, allowing blood to flow from the atrium into the ventricle. Now the cycle begins again. The cardiac cycle is generally divided into a diastole and a systole. Diastole refers to the relaxed ventricle filled with blood. Systole, on the other hand, refers to the contracted ventricle, which ejects the blood. Systole is divided into the contraction stage and the ejection stage. Diastole is divided into an early filling stage and a late filling stage. Electrical impulses are used to stimulate the heart muscles to contract. The cells that generate these electrical impulses are known as the sinoatrial node. Special muscle cells, shown here in green, quickly transmit the electrical impulses to the muscle cells of the atria and the atrioventricular node. There is only a narrow connection of muscle cells between the atria and the ventricles, known as the bundle of His. The atrioventricular node transmits the electrical impulses to the right and left bundles through these special muscle cells. Fast-conducting Purkinje fibers originate from the right and left bundles. These Purkinje fibers then transmit the impulses very quickly to the heart muscle cells of the ventricles. The sinoatrial node generates an electrical impulse, which is transmitted through the internodal tracts to the atrial muscles and the atrioventricular node. The AV node transmits the impulse with a time delay to the ventricles through the Purkinje fibers. The sinoatrial node is capable of generating 60 to 80 electrical impulses per minute. If the sinoatrial node fails, the AV node can generate approximately 40 to 60 impulses per minute. If the sinoatrial node and AV node fail, the bundle of His can still produce 20 to 40 impulses. For this reason, we speak of primary, secondary, and tertiary pacemaker cells. Let us now illustrate the path of the impulses in the human heart. The electrical impulses propagate in the atria and cause the muscles to contract, thus pumping the blood into the ventricles. The impulse is transmitted to the muscle cells of the ventricles via the AV node and the bundle of His. This causes the ventricular muscles to contract and pump the blood into the pulmonary artery and the aorta. The heart muscle cells have the special property of being able to transmit the electrical impulses to neighboring muscle cells. However, apart from the bundle of His, there is no connection between the atrial muscles and the ventricular muscles. For this reason, the atria and ventricles can contract at different times. The contraction of the ventricles begins at the apex of the heart. For this reason, the blood is literally squeezed out of the ventricles, similar to a tube of toothpaste that is rolled in from the back to the front. In medicine, electrical impulses can be used to check heart activity. This is done with the help of an electrocardiogram. The stimulation of the atria by the impulse of the sinoatrial node corresponds to the first wave. The stimulation of the ventricles through the atrioventricular node is represented by 3 spikes. The first wave is called the P wave, and the 3 graphical deflections the QRS complex. The last wave is the T wave, which represents the recovery of the ventricles. To allow the heart to change shape and size during contractions, it is enclosed in the pericardium. The pericardium consists of a semi-rigid outer layer of dense and loose connective tissue. A smooth layer is attached to this outer layer. Another smooth layer covers the heart. In humans, there is about 10 to 15 milliliters of fluid between the 2 layers, which serves as a lubricant. This allows the heart to change its shape and size in the pericardium without causing strong friction on the heart or other organs. Many more animations about the human body are available on this channel and my websites.